A rock is thrown upward on Mars with a velocity of 10 meters per second, and its height in meters t seconds later is given by h of t equals 10t minus 1.9 t squared. Find the average velocity for the time period beginning when t equals 2 and lasting 1 second, 0.5 seconds, 0.1 seconds, 0.05 seconds, and 0.01 seconds. Then estimate the instantaneous velocity when t equals 2. This is very similar to our example problem, except we are on Mars instead of at the CN Tower, and we are throwing a rock upward instead of just dropping it from the top of a tower. So we're still going to use the same method that we used before. We're going to calculate several average velocities over different time intervals and see if we can figure out what the limit might be to find the instantaneous velocity. Now, we know that the average velocity can be calculated by taking the change in position over the time that has elapsed. So let's start doing some of these calculations. We were asked to start at t equals 2 and look at a time period lasting 1 second. At least that's our first one. If it lasts 1 second, that means we're going from 2 seconds to 3 seconds. So the average velocity is going to be the change in position. So that'll be the height at 3 seconds minus the height at 2 seconds over the time elapsed. Well, we're going from 3 seconds to 2 seconds, or we're going from 2 seconds to 3 seconds, so we take 3 minus 2 to get that. Of course, the time that has elapsed is 1 second. For the change in position, we're going to have to evaluate these height function at these times. So we've got 10 times 3 minus 1.9 times 3 squared. And then we have to subtract 10 times 2 minus 1.9 times 2 squared. And again, I am just going to use a calculator for that. And I end up with 0.5. And this is going to be measured in meters per second. So the average velocity for that 1 second long interval is going to be 0.5 meters per second. All right, so that's the calculation for lasting 1 second. Now we need to do 0.5 seconds. So that's going to be the interval from 2 to 2.5 seconds. So in this case, the average velocity is going to be h of 2.5 minus h of 2 over 2.5 minus 2. And then we've got to plug in 2.5 there. So that'll be 10 times 2.5 minus 1.9 times 2.5 squared minus the quantity 10 times 2 minus 1.9 times 2 squared all over 0.5. And that ends up, when we plug it into a calculator, giving us 1.45 meters per second. So this is going to be a better approximation than the first one because we're looking at a shorter interval. But we can do better, and we're going to keep going. If we do the interval from 2 to 2.1 seconds, we need to do the calculation where we take h of 2.1 minus h of 2 and put that over 2.1 minus 2. And so we're just going to replace all of these 2.5s with 2.1s, and then the denominator is going to be 0.1. And to save time, I'm not going to write that all out. Instead, I'm going to plug that into a calculator, and I get 2.21 meters per second. And we can continue with the other intervals. If we go from 2 to 2.05 and we use a calculator, we get 2.305. And if we do from 2 to 2.01, again, we plug everything into a calculator. When I do that, I get 2.381. And I'm going to be honest, I can't see exactly where this is going to stop, what this limit is going to be. Because we started at 0.5 and we eventually got above 2, 2.305, 2.381. This is still a big jump, so I'm going to continue, which is what we do when it's not clear. And I'm going to look at the interval from 2 to 2.001. And here our average velocity, when we do all of those calculations, is 2.3981. It looks like we are starting to slow down in our growth. I'm going to guess 2.4 meters per second. But I'm going to do one more calculation, adding in another 0 here. And when I plug all that into a calculator, I get 2.39981. So we are eventually seeing a pattern when we're going to a very, very tiny interval. This is only 1/1000th of a second. The average velocity is getting very, very, very close to 2.4 meters per second. And so it does, in fact, look like that is what the limit is going to be. So that is what we can expect the instantaneous velocity to be at t equals 2.